rational? Ratio. And what's a ratio? Yeah, exactly, right? It's been a while, probably. This is back in pre-algebra, algebra 1. Ratio, if you have like P to Q or F to G, you can actually write F in the word to, and then G. You can write F with a little colon, G, or you can write F much more commonly over G. Anyway, ratio, rational functions, ratio, we're talking about fractions. Rational numbers, numbers that can be written as fractions. 5 is a rational number. Why? It can be 5 over 1. 2/3 is a rational number. Why? It's a fraction. 0.5 is a rational number. Why? Exactly. Root 2 is not a rational function. Why? You can write it as root 2 over 1. Yeah, but the root's still there. Can't be simplified to just a fraction of whole numbers. Root 4 is a rational number because it can be rewritten as 2 over 1. Anyway, rational functions, rational numbers, ratio fractions. Long story short, fractions have, well, at least for the beginning of this, problems in the denominator, right? Since the beginning of the year, the domain, there's a domain problem. There is a problem in the domain whenever you have a denominator that can be 0. That can be 0. Can anyone think of, just really quickly, a fraction or a denominator, bless you, where there is an x? Let me just put something on top, something random. What's a denominator that couldn't be 0? Okay, that's true. That's true. What's the domain of this? All real numbers. Why? Because 2 can't be equal to, what's the problem? Denominators can't be what again? Okay, so 2 can't equal 0, so domain is all real numbers, right? So we could say domain x is within, how do we write all real numbers in intervals again? Good. But I was actually also asking for, I'll do another random numerator. What's a denominator that also can't be 0 but has a variable in it? What, Matthew? What's another denominator with a variable, with an x, that can never be 0? X squared can be 0, though, when x is 0. Keep thinking. 6. 6x can be 0 at 0. X plus 1 can be 0 when x equals -1. 2/3, no, it's still when x is 0, though, right? What's a denominator that can never be 0 but still has an x? No, it can still be when, well, that's always 0. That's even worse. That never works. Negative x? No, because that's still at 0. Oh, we did section 2.4. What was section 2.4? Imaginary numbers. How can we put something down here that will only be 0 at an imaginary number so it won't really ever have a problem? Yeah, so give me a factor with a negative square root as a 0. We could build it that way. We could do like an x plus 4i, x minus 4i. But does anybody remember where the 4i's came from? What was in the factors where the 4i's came out of? That's what came out of it. No one remembers where they came from? Yeah. So how do you get a square root of a negative? What was going on over here? Couldn't we square both sides? Right? I'm just going to put a negative y. Right? What would have been down here? Replace this with a number. What do you guys want? Sure. There's a denominator. I actually kind of gave you a hint. The numerator only has imaginary zeros also. That could have been one. Because if you tried to find the zeros, what's going to happen? They're going to be imaginary. So anyway, just because there's a denominator does not mean for both these functions the domain is all real numbers. Just because there's a denominator does not mean there's a domain restriction, but the exception is that the bottom can't be 0. What normally happens? There are zeros in the denominator. And those zeros are called discontinuities, and there are two different types, okay? Here we are, two different types of discontinuities, aka places where the denominator equals 0. We fixed it should be f of t, not f of x. Did you guys change it yet? It should be f of t, not f of x. So how did I get -1? Where was I looking? Numerator, denominator, or both? Yeah, I was specifically looking at the denominator. Good. For the vertical asymptote, how did I get x cannot equal? Ooh, that's a typo. How did I get x cannot equal -2? Where was I looking? Numerator or denominator? Okay. Do you guys notice, did anyone notice that I could have gotten -1 from the numerator also? Because how can I rewrite that numerator in factored form? What would that be? T minus 1 and t plus 1. What do you notice about the numerator and, yeah, well, it's technically, what's the word? Not cancel. That's like 5 minus 5 is 0. Factor out and disappear. Kind of. But vanish, is it vanish to 0 or vanish to 1? Vanishing to 0 is cancel. Vanishing to 1 is reduce. Ah, tricky, tricky, tricky. So yeah, you can reduce this away. But here's the idea. When you do reduce it away to be t minus 1, we have to maintain that from the very, very beginning, t could never equal never equal -1. So even though we are able to reduce it away, we can't automatically be like, oh, so it was never a problem? Yes, it was. You can think it leaves scars, if that helps. We know that traumatic things in life leave scars, right? Doesn't mean they're all bad. Doesn't mean that God can't heal us through those scars, but traumatic things leave scars, so do denominators. Like even if you can get rid of them, there's still the scar of, ooh, okay, hold on. I can write that f of t is t minus 1, but I have to maintain that t still cannot equal -1. But maybe just a few of you guys can see how I got the graph, because I was talking to you guys on Friday. But hopefully by the end of this section, you'll be able to do kind of what I did in sketching these two functions really quickly. Maybe not really quickly, but you'll be able to without a calculator. How was I able to graph this function which has an intercept of -1 and a seemingly slope of up 1 over 1? It's a line. In my head, I factored, I reduced, and I figured out who was left, and I said, hey, that's an mx plus b. And so I made my intercept, and I made my slope, but wait a minute, who's this guy, and why is he there? Well, guys, can you tell what point it seems to be? What point is that? Do you guys agree? Hold on. Graphing points. This is like pre-algebra, right? Graphing points, do you guys agree with -1, -2? Yeah. Okay. Jason agrees. Matthew agrees. The rest of you guys are asleep. So -1, -2? I think Joe agrees too. The rest of you guys good? How can you get the point -1, -2 from this function? What happens if we plug in? Not just 0, it's even worse than that. Yeah, if you plugged in -1 from the very beginning, we would actually get 0 over 0. Well, that's not good. But what did I just say this is the exact same thing as? So what happens if we plug in over here? What would f of -1 now be? Now, it's not allowed to be it, but where would it be at? What's -1 minus 1? -2. Yeah, my negative got a little disappeared. My negative disappeared a little bit there. I apologize for that. But you would get the point -1, -2. Not from the beginning. At the beginning, we get 0 over 0. But at the end, after we factor and reduce, we could go ahead and plug in and get -2. And we'd have to put an empty hole there. because it's not allowed, it meaning the function is not allowed to actually be there. Y equals x minus 1. There we go. The function is not allowed to be there, but I can tell the location after I factor and reduce. Now, guys, hold on. Just go with me for a second. What happens if we plug in the domain problem down here to the vertical asymptote? What happens if we plug in -2? You get a 0, but where? In the denominator. What do we get in the numerator? Three? Are you guys sure? 7 plus 2 times -2 is -4, right? So then that'd be 3 over 0. I wonder if that's a pattern. Let's keep going. We're going to talk about vertical asymptotes just a little bit, and let's see if maybe this pattern might repeat itself anywhere between holes and vertical asymptotes. But for right now, what I want you guys, if you have a colored pen, here might be a good thing to highlight. My orientation is just a little bit off. Sorry, I'm still getting used to it. With holes, removable discontinuities, the denominator can be factored out, specifically factored and reduced. Not just factored, but reduced, because the factor is shared. But for non-removable discontinuities, aka for vertical asymptotes versus holes, it can't be factored and reduced. Now, just a few of you out there might try to do some reducing here. Is it illegal or is it not illegal to say, hey, there are 2's that are shared and x's that are shared and pluses that are shared. This just equals 7.
It's illegal.
Doesn't make sense. But just a few of you see things like x's and 2's and pluses, and you just want to cancel it all out. Now, some of you, actually most of you, know better than to cancel everything out. But you still do some sort of magical reducing. What happens, what gets killed when you start randomly crossing things out when the factors are not shared? Not seals. Seals are distributing. Kittens, yeah. You have to check the numerator denominator. They must be completely the same in order to reduce. Like t plus 1 over t plus n, t plus 1. They were totally the same. Those can reduce. These cannot. Okay? So the difference between being able to reduce and not being able to reduce is whether or not the factors match. Okay. With that, sorry guys, you can't read the top of that page, can you? We're going to talk about behavior. And technically, I'm going to show you with graphing calculator language how we can see what's going on near a vertical asymptote as far as whether the function is coming in and swooping up or swooping down. Because we're looking at harder functions than 1 over x. This one over here, 7 plus 2x over 2 plus x. That's a harder function than the parent function 1 over x from section 1.6. And so to be prepared for those harder functions and reminding ourselves, or actually maybe just reflecting on the fact that I want you guys to be able to sketch these by hand, bless you, by the end of class or by the end of this section. We got some work cut out for us if these functions are going to get nasty. So this is one clue. Finding the discontinuities, the domain. Bless you, whether it's a vertical asymptote or a hole, identifying that. That's one clue. That's one thing that'll help, but then behavior near vertical asymptotes, that's another thing that's going to help. I'm going to remind us really quickly of 2 parent functions. Actually, you only saw one of them, but the other one's one that calculus memorizes. We learned this parent function back in section 1.6 before we did all the reflections and transformations. But I'm going to also show you 1 over x squared, which looks almost the same in its general pattern, its general behavior. But why is it different? Can anybody tell why 1 over x squared is different than 1 over x? Yeah, why aren't they on opposite? This one has origin symmetry. This one has y-axis symmetry, but why? What's the vertical asymptote for both of them? You guys agreeing with Matthew? Matthew, you're doing a great job, bud, but I'm going to quiet you down for a little bit, okay? Let's see if anyone else will speak up. Why is the vertical asymptote at 0? What do they both have in the denominator? X cannot be 0. Yeah, that's true. They both have the restriction x can't be 0. But what's different between the power of x here and the power of x there? That one's squared. This one's to the single. My domain for both of them is x cannot equal 0. X can be negatives or x can be positives. What happens when I plug in positives to this one? What kind of number do you get out? True. But hold on. Guys, listen carefully to what I'm asking. What happens when you plug in a positive? What do you think I'm caring about? How big the number is or the sign of the number? Yeah. So what happens when you plug in a positive? Plug one in your head if it's too hard. 1/2, 1/3, 1/4, 1/10. What happens when you plug in a positive? What kind of number comes out? A positive number. Thanks, Wesley. What happens when you plug in a negative? It's a negative. Okay, what's different over here? It's all, oh, so the y's can never go negative? Okay. So this one, the y's can go negative and positive depending on what x is when you plug it in, what sign, what nature of x, positive or negative. But this one will always be positive because it doesn't matter what you plug in for x. As long as x doesn't equal 0, always positive. Now, what's this guy going to look like? Maybe some of you guys could guess. Maybe some of you could remember section 1.7, transformations. I think this one is shifted, and I think he's a bit reflected. And maybe you could figure out from parent functions. But since we're getting ready for harder functions, I'm going to go ahead and show you how, without even considering those, we can think of what's going on as you come towards the vertical asymptote. Thank you, Joe. Let me zoom in. I said just a second ago, even though some of you might be able to think of the different clues and tricks from transformations, I'm going to show you how you don't even need to consider those basic parent functions because it's going to get a lot worse. So I want you guys to go ahead and draw for me 4 different vertical asymptotes. If I can make room. 4 different vertical asymptotes. I'm going to show you the 4 different types of behaviors that can be happening as we come in towards the vertical asymptotes. There's only 4. One is you could have going down, going up, or you could have going up, going down if there's been a reflection, or you could have going down, or you could have going up, going up. Thank you, Sina. Those are the 4 different behaviors. That's it. As you come towards the vertical asymptote, are you allowed to hit it? Yes or no? No. No. So it has to somehow skim, and in order to skim, it either has to go up or it has to go down. It meaning the y values. So the function approaching a vertical asymptote is either going to go, wait a minute, how can we explain mathematically how the function's going to behave? Either it's going to go, in words, down, falling, or go up, rising. But what's the notation for that? Yeah, negative infinity or positive infinity. When we're talking about behavior near or towards coming into vertical asymptotes, the function's either fallen or it's rising. And so here's an example function. The function's either rising or it's falling. That's it. 2 answers, negative infinity or positive infinity. My question as we come to this example, first of all, is just what's my domain? X cannot equal... Good. The bottom can't equal 0, right? So if we solve that, x can't equal -1. A question, is it a vertical asymptote or a hole? Pause. Read your notes. Pause. Read your notes. Holes are which ones?
It's vertical asymptote.
Hole. I don't care. I don't care what that you just guessed a different one. I care what your notes say. So, question. What do your notes say about holes? Whether the denominator can be factored out and reduced, right? So, question, can I remove x plus 1? I can't just magically make it disappear? And there's nothing matching it in the numerator that can let me get rid of it? So therefore it's non-removable? Ah, and what do your notes say about non-removable discontinuities? Ah, there we go. So this is for sure a vertical asymptote. It's only going to be a hole. This domain problem is only going to be a hole if there's an x plus 1 on top that can reduce. You mean both going down? Well, it wouldn't be a 1 over x because that one is able to go both directions. If they're both going together, it would be like a negative 1 over x squared. It'd be a reflection of the second one, not the first one. If this one flips, they're not going to both be going down. If this one flips, if you multiply by a negative, it will always have the negative. Does that make sense? Yeah. Okay, so coming back. Can you guys help me out real fast, though? What would, if we did try, what would happen if we plugged in? That's weird. What would happen if we plugged in the discontinuity of negative 1? This one right here. What if we plugged in negative 1? It's a domain problem. I get it. No, only one part 0. The bottom 0, what's the top? Okay, pause real quick. I just want to show you guys a trick. The whole removable, non-removable thing is super important, mathematically speaking, because holes, we want to factor and reduce to be able to see where the hole is. We have to plug into the reduced form, not the original form, to find the hole. Vertical asymptotes can't be reduced. That's part of their definition, where they come from. But here's a quick little trick, okay? If you have a highlighter, it might be a good idea to make a quick note of the fact that if you have a vertical asymptote, again, you'll always get number over 0. If you have a vertical asymptote, when you plug in, you'll always get number over 0. If you have a hole, guess what you get instead? Always a 0 over 0. Why? Zeros are shared. Now the top, the top's going to depend on what number they give you. But the cool pattern, the cool trick is vertical asymptotes will always equal number over 0 when you plug in, whereas holes will always be 0 over 0 when you plug in. Because if factors are shared, then the zeros are the same top and bottom. Super silly, I know. It might not seem super important. It comes back in calculus. Maybe some of you will use it. Maybe some of you will not. But the idea is, if you plug in the discontinuity to a hole, a trick to remembering is that you will always get 0 over 0. And if you plug into a vertical asymptote, you'll always get number over 0. It's something for really hard polynomials that can actually make life a little bit easier. Let's come back to the behavior part, though. Okay, we have this function. We've figured out it's a vertical asymptote. It doesn't factor and reduce. It plugs in to be a number over 0. Now what? Okay, if I allowed you to use your graphing calculator, and if there was time and it wasn't chapel day, all right? Do you guys know why I have the ask feature selected on the table setup, which is under second window? What do you see the numbers doing? Yeah, well, I'm trying to show the idea of getting closer and closer but never touching it. Now, hold on. The calculator said it was -1, but it's not. I don't get it. Oh, there's only so many place values, so it rounded. But do you see me getting closer and closer to -1? Okay, so if we're approaching, x is approaching -1 from below. Wait, from below. Hold on, number line, help out. -1, 0, -2. These numbers right here, is it from above -1 on the number line or from below? From -1/2, -0.9, -0.99, -0.999. Is it above -1 or below? Above. Good, because number's a little bit more positive. So I could put my negative 0.5, I could put my negative 0.9, I can put my, I keep on getting closer and closer, but long story short, this would be from above. So we could say, as x approaches negative 1 from above, f of x is approaching. And then this one must be as x approaches negative 1 from, does it make sense? This one's from below, guys? Where's negative 2, negative 1.1, negative 1.01, right? It'd be getting closer from the other direction, approaching from the other direction. So we could go to our graphing calculator and we could actually plug in these numbers and we could see what's going on. So we came from above, we came from below. I already had my graphing calculator all nice and set up and I copied the windows in. What my question is to you guys, can you fill in what f of x is approaching? What the y's are approaching? Look up above. What are the two answers that are possible from the 4 graphs that we look at or from the 2 answers that we wrote? Our 2 answers are either negative infinity or positive infinity. So from this table, let me zoom back in. Those are the only 2 answers we can possibly even put for vertical asymptotes. Where are the y's approaching on this guy? From above the vertical asymptote. Yeah, because isn't e to the 5 times 10 to the 5th? Isn't that negative 3 with 5 zeros after it? Where are these guys going? From above, negative infinity. And what's going on from below? Positive infinity, because they're going higher and higher and higher. So long story short, right now, without knowing much else, I can say for you guys, if we were to go to negative 1 and put a vertical asymptote, I know somehow this guy from above is going to be going down, and somehow from below this guy is going to be going up. Do we know everything? No, we have a few more clues to talk about. But we do know around the vertical asymptote, what's the behavior? From above, negative infinity, from below, positive infinity. Now some of you are like, oh, hey, it's that guy shifted left 1 with a vertical reflection. Yeah, you're actually pretty good on that if you thought through that. That's what Joe was saying earlier. But once again, I'm getting you ready for harder things and harder functions. So let me show you the exact same problem, but in a way that we didn't have to deal with, or we don't have to use our calculator, and we don't have to even think about the 1 over x over there. Okay, let me show you a trick. How to do this by hand. How to figure out whether towards the vertical asymptote we're going up, we're going down, or we're going the other 2 directions. With math, without a calculator. With math, even on functions that are way nastier than the 2 up at the front. We could come from above the vertical asymptote, and we could come from below, actually really easily. Filling in x approaches negative 1, f of x approaches, and as x approaches, which this is going to change based on the function that we have, but for this one, because our domain was x cannot equal negative 1, that's the guy that we're going to. We know from the very beginning that our answers are either positive infinity or negative infinity because we already talked about how we could tell this is a vertical asymptote. Here's what I need you to do. I need you to think through what is a number above. If we had our number line, what's a number above but barely above? You just saw a lot of them in the table. Give me 1. What's 1 that's above? Negative 0.9? Matthew, what'd you say? Oh, we're doing a lot of them. Okay, well, I don't want to go continuously. I'm just going to choose one number. So I'm going to choose negative 0.9. And we're going to use that representative number to plug in. Plug into what? Plug into our function. So we could go ahead and say f of equals negative 3 over, we're just plugging into our function. We're going to do the exact same thing as we come down here coming from below. Except, what's a number that's a little bit below -1? No, -0.8 is actually way up here by 0. -1.1, that's a little better. Okay, so we have -1.1 and we have -0.9. So I'm going to put in -1.1. I'm going to plug in -0.9. Which, some of you are like, oh, this is disgusting. Like now there are fractions and there are decimals. But hold on. All we care about is positive or negative. All we care about is positive or negative. So the hint is going to be check the sign. If you're doing behavior by hand without a graphing calculator, just check the sign. If you were to plug into the numerator of this guy, well, there was nothing to plug in, so it's going to be a negative number. If you were to plug into the denominator, which is what we did, what's -0.9 or -0.99 or -0.999 plus 1? All of those numbers are going to be positive. And a positive divided by a negative is going to be a negative. Hence, I'm going to answer with a negative infinity, and I didn't even care about the value. Down here, when I plugged into the numerator, well, there was nothing to plug in, so I had a negative. When I plugged into the denominator, 1.001 plus 1, those are all negatives. And what's any negative over a negative?
Positive.
You don't need a calculator. All you need is one representative value from above, from below, and check the sign, positive or negative. We've talked about discontinuities. We've talked about holes versus vertical asymptotes. We talked about how you can at least get an idea of what's going on as we go in towards the vertical asymptote. The problem is, if you were to look at the backboard, there are two different types of asymptotes that we still need to talk about. Vertical asymptote is one type. But what about horizontal asymptotes? Vertical asymptotes, that's one type of asymptote. But there are two other types of asymptotes, horizontal and oblique, aka slanty ones. Let me give you a second to get this down. Skip me one line in between, everyone. Okay, just skip one line in between. Nice thing is, this is Algebra 2 review. Nice thing is, this is Algebra 2 review. No, not for Chapter 2. So what's going on with the horizontal asymptote is that the y values are getting closer and closer and closer to L is just a constant. So instead of coming in towards an x value, once again, we're going out to the infinities. And you guys talked about these. We talked about these back in Chapter 1 with end behavior. So this is going to the left, if we were to use our words, to the right. But I just need to help you guys review real fast how we find horizontal asymptotes. So we compare the degrees of the top and of the bottom, of the numerator and of the denominator. I just call them top and bottom. This is a little bit faster, a little bit easier in my head. And the degrees, remember, are the highest power of x. So if the degree of the top is greater than the degree of the bottom, if we were to do like a long division, if the degree of the top 1, we would get a polynomial out. And all polynomials somehow go to infinities, however you do it. Both up, both down. So if they both go to infinities, there's no horizontal asymptote tying it down. So there's actually, if I was to fill in horizontal asymptote, the answer would be none. I'll just say no HA. No horizontal asymptote. And the way of remembering that is really quickly, if the top wins. If the top wins, there's no horizontal asymptote. The second one says, what if the bottom wins? If the bottom wins, we can't even really do long division because there's going to be nothing left. And maybe that's a way of thinking about it. If the degree of the bottom wins, it's a fraction that's smaller than 1. And what's going to end up happening is actually As you go to infinity, the denominator wins more and more and more and more and divides it more and more and more and more. It ties it all the way back to 0. It holds the function in. It keeps it confined. So instead of being able to go to infinity or negative infinity like a numerator would want to do as a polynomial, the denominator is going to pull it all the way back to 0. And the last case says, well, what if there's a tie? What if the degree is the same? If the degree is the same, you also have a horizontal asymptote, because that function's not going to be able to go to positive or negative infinity like it would like as a polynomial. But it's also not going to be tied all the way back to 0. It's going to be tied instead to the ratio of the leading coefficients. And I think as you guys look at examples, I think as you see this in homework, you'll remember the degree test from Algebra 2 and how to find horizontal asymptotes. I don't think that's going to be too crazy for you. You've seen vertical asymptotes before. You've seen holes before. Horizontal asymptotes with the degree test, you've seen that before also. So I'm going to leave you guys to peek at examples of that one as far as how to solve. The one I'm not so sure that you're going to totally be okay with is one called a slanty asymptote or an oblique asymptote. So just before class is over, before totally sending you to homework, we're just going to ask you guys to get at least halfway through again, kind of like we did with section 2.5. They're hard sections. So I'll give a little bit of grace for the deadline tomorrow, at least halfway. I want to give you a hint about this one called a slanty asymptote. A slanty asymptote only happens when the degree of the numerator is only 1 higher than the degree of the denominator. And if it is, we do a long division, how we plug in the polynomial. And as we plug in, we just need to, here's my hint, ignore the remainder. You divide and ignore the remainder. So then in this example, after you divide, there's going to be an oblique asymptote at your final answer. You guys can go ahead and pack up. But whereas normally we would write the remainder with long division, you actually ignore that and you just steal the whole part, and there's going to be a slanty asymptote. It rarely happens. It only happens every now and then. I'll leave you guys to try to find them in your homework. It only happens when the top wins by 1. All right, kiddos, go work on homework. You're playing around with vertical, horizontal, oblique asymptotes. We'll go over questions tomorrow. Hopefully you'll be a little more alive tomorrow, too. It was a struggle today. Yeah.
You said that we